Okay, so let's get to the plots now. You notice the document has changed a little bit. I've done some upgrades. All right, the first plot is A here. And what you want to do is, again, you're going to put your sensor1 function in a Python file and use this sensor1 function called this way in your program to make these plots. All right, so you're going to plot minus log of 0 count over m as a function of d. For these values of d, you use L equals 1,000, and you'll plot different series for these values of m. And for each value of m and d, run the simulation 5 times. So you should treat all points pertaining to a given value of m as a single series. Plot these 5 series of values as data points, not as lines. Use a different color for each series. You may plot also the theoretical value as a dotted line, which is d. This can be proven using Bernoulli trials. All right, so what's going on here? You're going to have a graph like this. Now, for each value of m, you have a different series. Remember, you're going to have, oops, let's see if this is working. Oh, all right, good. So, say for m equals 25, you're going to have 5 values for each value of d. So, let's see if I can make this work here. So it's going to look something like this. You have 5 values there, 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 5 values there. I'm not sure what it's going to look like, but that's what that should look like. Then for m equals 100, you'll have 5 values here, 5 values, I don't know, 5 values here, 5 values here, etc. Then also you're going to have the theoretical value, d, so just to make a dotted line across like this. All right, so that's pretty much what your graph should look like. Now, what's the usefulness of this graph? 0 count over m is the estimated probability that a randomly placed sensor will cover no targets at all. All right, because 0 count is the number of sensors that miss everything, and m was the total number of sensors that you place. Now, this is an experiment, and there's going to be some variation between experiments. But on the average, this number should average out to the actual density. Right. Now, these results also show it's possible to estimate the density of random points along a line by randomly scattering sensors along the line, as explained below. So here's a question. I want you to answer these questions in a Word document that you can put on Dropbox. Notice that the theoretical value of this quantity is the density. So if we do scatter sensors and we do a 0 count and we compute this quantity, we should be able to estimate the density. So here's the scenario. Suppose the Department of Interior wants to estimate the mean density of skunks. I don't know if you noticed, but there are a lot of skunks this year along a road of length 100 kilometers. That should be 100, not 100 kilometer meters, it's just 100 kilometers. Right, the DOI has a large number of low-cost skunk sensors that can detect skunks along a 100-meter stretch of road. Okay, those skunk sensors are automatic. They're not people. They're something that can possibly detect the scent of a skunk for 50 meters. 50 meters in each direction would make 100 meters. Okay. So notice that the sensor length is 100 instead of 1, but the total length is 100 kilometers. So 100 kilometers means that's 100,000 meters. So still the length of the road is 1,000 times the length of the sensor. So the sensor is not able to detect the number of skunks, but only whether or not there is a skunk. So the DOI is able to scatter these sensors randomly by air. So they're just scattering them randomly. So this matches our scenario of points, which are the skunks, and intervals, which are the sensors. So based on your graph above, and other numerical experiments if you want, estimate how many sensors you recommend they scatter if they want to estimate the mean density of, that should be skunks. Change the scenario in the middle, so that should be skunks, sorry. Well, done. I mean, they don't have to be so. All right, now, how are you going to tell this? Well, if you look at your graph, you can kind of look at the scatter. You can see how many sensors you need in order to have less scatter. Right? So if there's a lot of scatter, then then that number of sensors is not going to give you a very accurate estimate. So that's what you can look at. And you want to estimate the density of skunks to within 0.02. That's not percent, that's just the value. So that's 2%. So I can just say that's 2%. Well, all right, so that's the first thing. That's the first simulation that gives us some results that could potentially be practically significant. Okay. Next simulation, so this would be another code or another section in the same code. So we're plotting uvec.size over n as a function of density, but same values to density. We'll use L equals 1,000, but we're going to use a lot more simulations. So this is going to take longer to run. For each value of d, run the simulation 3 times, plot these results as points. Altogether, the plot should have 18 points. Now, in this case, you don't have a different series for different m. M is fixed as a function of n and a function of d. I'm sorry, as a function of n. Now, n, you obtain n as a function of d, but m does not vary, so you don't have different series. You only have one series. You're going to have 3 points for each d. So that will have 18 points altogether. You can make them all the same color because you're not really plotting different series. Now, the theoretical value is 2 minus e to the minus d. So this also is a calculation that you get from probability theory. So add a title, legend, and x and y labels. Now, what's the significance of this graph? UVec gives all possible subsets of point vec, which are the number of random points, that can be covered by a single unit interval. Right? If the 2 points are too far apart, they can't be covered by a single unit interval. So there's certain number of sets, certain limited number of sets of points that can be covered by a single unit interval. The problem of finding a smallest possible set of unit intervals that cover point vec consisting of, let's see, set of unit intervals that cover point vec. So this should be out here. Sorry, editing as I go. Is equivalent to the problem of finding the smallest subset of UVec whose union contains all of PTVec. So UVec, remember the elements of UVec represent intervals. So you want to choose some intervals that cover all the points. And you want to choose as few intervals as possible if you want to use as few sensors as possible. Thus, UVec size gives the number of options we must consider. These are the number of different ways that sensors can fall among the different points. So this gives us some idea of the difficulty of the problem to finding the smallest set, because these are basically the number of options we need to consider. So I gave you the theoretical value. So the question is the theoretical value accurate over the entire range of d? If not, where does it fail? So I haven't actually tested this. I believe this is the theoretical value, and we'll see how good it is. So you can make some, so I'll just say make any other appropriate comments. So that's the second one. Third one is very similar. In this case, we did UVec, we did U size over n. UVec is the possible subset of PTVec. The reason I divided by n is I want to control the size. You know, if you double the size, if you double the length, double the size, you would expect this number to be doubled. So I'm scaling it so it's going to be a reasonable number. Also, because when I scale it, when I divide by n, the theoretical value is this. So the theoretical value of uvec.size is n times this value. So I've kind of divided out the n, so that's no longer an issue. Okay, so I'm going to do the same thing with maxvec. Now, maxvec is like uvec, except it only counts the maximal intervals, and those are the intervals that contain as many points as possible. An interval is maximal. You can't find an interval that contains more points, that contains all those points plus more points. If it's not maximal, you can find another interval that does contain all the points in that interval plus more points. Now, this theoretical value is a little bit different. I think I computed this right, and you'll find out. So this plot is very much like the other one. So I actually want you to plot this on the same I want you to plot this on the same axes. I think I said that. Okay. No, I guess I didn't say that. Let me see if I want to do that. Hang on a second. Okay, there I just changed it. So plot these on the same axis as the previous problem. Right. So what I say here about the significance is that if we want to choose our intervals intelligently, we will be choosing intervals that are maximal. So this gives us the number of options of maximal intervals options that we need to consider. So also same question, does the theoretical value accurate, or does it fail somewhere? All right, so next one, I want to plot the mean of max set count over mean of set count and subtract 1. And that's a function of d. And I want to use the same parameter values that you used in the 2 previous questions. So you're going to get one series, one color, but you're going to get 5 values. I think it was 5 values, right? Did I say 5 values? Oh, 3 values. You're going to get 3 values for each value of d. So what's the significance of this plot? If we scatter sensors randomly, the question is, are you more likely to get a maximal set than some other set? Are maximal sets more probable than other sets? So this gives the ratio of the probability of a typical maximal set to the probability of a typical set. So if this is greater than 1, that means that you're more likely to hit a maximal set than otherwise. Now that's good news, because if you scatter sensors randomly, you want to hit maximal sets. So we'll see if scattering random sensors is a good strategy or not. All right, now last one. I think this is the last one. Yeah, it's the last one. All right. So last one says, using count max point vec, count the number of points in point vec that are in only one maximal set. Okay, so and plot this value divided by n as a function of d using the same parameter values that you used in the previous 3 questions. Give title and label x and y axes. So what are we talking about here? You're looking in PTVec, and PTVec, when you do the simulation, PTVec is in some of the sets and is not in other of the sets. So count max PTVec is going to count the number of points that are in only one maximal set. I should say exactly one, not only one. I should say exactly one. So you should be able to do that because you look at your count max point vec and you look at the ones that have entry 1, and those are the points that are in exactly one maximal set. So I want to plot this value divided by n as a function of d using the same parameter values that you had before. All right. So what's the significance? If there's any point that's in only one maximal set, then if I'm looking for a best cover for all of the points, then that maximal set must be in the cover. All right, so I can simplify the problem. Now, if there are lots of points that are in only one maximal set, then I can simplify my problem considerably because I don't even need to consider those maximal sets. I know they have to be in the cover, and then I can only consider the remaining points and the remaining maximal intervals, and my problem is that much simpler. All right, so these are just some problems searching for characteristics of this general problem of intervals covering points. And that's it.